Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
Welcome to Trigonometric Identities. So one of the reasons that we practice trigonometric identities is so that we can simplify our future application problems. Okay, so that is really going to be the one focus. So it's going to simplify future problems, especially in calculus. And so just getting practical practice with these, getting used to manipulating them can really help us out. I like to put everything in terms of sine and cosine. And the reason I like to do that is I think it just makes them a little bit easier to work with occasionally. And our goal with some of these problems that we're going to practice today is to reduce it down to a single trig word. Again, that's that whole simplification to make future problems easier. Okay, so let's just go ahead and jump right into it. Hopefully you know some basic identities at this point. If not, you might go back, practice some of your geometry, things like that. So our first problem is going to be simplifying the cosine of t plus the tangent of t times the sine of t. Now, it's understood that there are parentheses around these variables. And again, if you haven't practiced with them, cosine, sine, tangent have to have a variable inside of them or an angle, one of the two. So in this case, we have t. I've drawn my t's like this just so they don't look like plus signs. So I'm going to go ahead and switch to that strategy of putting everything in terms of sine and cosine. I have a sine and a cosine, but I have a tangent here. Hopefully you've learned that tangent is equal to sine over cosine. And you might say, well, Michelle, that did not look like it simplified it anything. And you're correct. It really didn't. But let's go ahead and let's look at the second term, and then we're going to talk about combining these two terms, because we would like one term. So we have the cosine of t. When I put this over 1, I can multiply my fractions, and I wind up with sine squared over cosine, which, still doesn't look like it's going anywhere. But when we think about fractions, we know that in order to add fractions, we have to have a common denominator. So since this has a cosine t denominator, I'm going to multiply top and bottom by cosine of t. When I multiply the numerator by cosine of t, that's going to end up making it cosine of t squared. Now, hopefully, you might remember your Pythagorean identities, because cosine squared of t plus sine squared of t simplifies quite nicely. Here's that common denominator of cosine of t. So when we look back and we think, hey, what does cosine squared plus sine squared equal? Oh yeah, that was one of our Pythagorean identities. And it equals 1. So this actually gives us 1 over the cosine of t, which can finally now be simplified into secant of angle t. So we went from a binomial, where we had cosine plus a product of tangent and sine, to a single word, and that is secant. And that's going to be kind of the idea and the theme here, is to take a problem that looks complex and take it down to a single trig word as much as possible. Won't always be able to do it, but we're going to try. So let's simplify sine of x divided by the cosecant of x plus cosine of x divided by secant of x. Okay, so let's break that down. Going back to our terms of sine and cosine, we have some things that are not in terms of sine and cosine, so that's the first thing I'm going to work on. So I have the sine of x divided by cosecant, which is really 1 over sine, plus cosine divided by secant, which is 1 over cosine. And I wrote it like this because I knew I was going to have fractions, and I really don't want a fraction inside a fraction. However, if you recall, dividing fractions, you use the multiplicative reciprocal, so this will become the sine of x times the sine of x, or sine squared, plus the cosine of x times the reciprocal, so cosine of x, which would be cosine squared. And if you recall, we just talked about this. This is a Pythagorean identity. Sine squared plus cosine squared is 1. So the original problem reduced to a factor of 1. Our next problem, we're going to simplify 1 plus cosine beta and 1 minus cosine of beta. Now I understand that sometimes the trig words can get a little complicated, so I'm going to use another strategy that I sometimes use, and I'm going to do a similar problem, but I'm going to make it look a lot more algebraic. I'm not going to write the entire word down. I'm just going to write down the C for cosine. You do need to be careful with this because you have multiple trig words. It could get confusing. But many of you have taken a problem of 1 plus c and 1 minus c and went ahead and multiplied that binomials out in your Algebra 1 and Algebra 2 class. It would give us 1 plus c minus c squared, which would then simplify to 1 minus c squared. So reversing that back and going back into our trig words, when I multiply 1 plus cosine beta times 1 minus cosine beta, I would get 1 minus cosine squared beta. Okay, well, here comes that side note. Thinking about cosine squared beta, we know, and we've talked about the fact that sine squared of x plus cosine squared of x equals 1. So sine squared by itself, I would move the cosine squared over. Okay, so we have something similar. We just have beta instead of x. So 1 minus cosine squared of beta can be reduced to sine squared of beta. So that Pythagorean identity is going to be coming in a lot. If you don't understand the Pythagorean identity, I truly, truly recommend that you go in and you delve into why that's true. But going ahead and showing these and simplifying these are not too bad as long as we're replacing tangent, cotangent, secant, cosecant with sine and cosine of their equivalency, and it should keep things going for us. So we are going to move into proving trigonometric identities and disproving. Disproving is simplest. It really is very easy. So sine of x plus cosine of x equals 1. And we're going to go ahead and we're going to prove that this is not true. Okay, so we are going to disprove. This is a false statement. And the reason it is false is we are going to give a counterexample. Counterexample is a great way of disproving something. So I am going to pick a 30, 60, 90 type triangle, and I'm going to use 30 degrees. Okay, have my triangle drawn. So the sine of 30 plus the cosine of 30 would be 1/2 plus the square root of 3 over 2, which is going to equal 1 plus the square root of 3, all divided by 2. Now if I go ahead and look at that on a calculator, that's approximately 1.366. Which does not equal 1. So we have now used an example to prove that this statement is false. So disproving something is super easy. You just need to do a proof by counterexample. Just find an angle that doesn't make it work, substitute it in, show that it doesn't work, and you're great. Now, to prove something is true, and we are going to do this a lot with the rest of this video, they're going to give you a left side and a right side. Okay, so we'll call this side f of x, and we'll call this side g of x. And they're going to say, prove that f of x equals g of x. You have two options. You can work f of x until it becomes g of x. You can work g of x until it becomes f of x. Or you can work both sides. It depends on the problem. And I know some people in geometry remember that proofs had the whole two columns and you had to state your y every single time. I'm not going into a proof like that. I'm just going into a show your work to show that this is true. You don't have to write down, I multiplied both sides by this, I did this to both sides, I substituted an equivalence. We're not worrying about that in this video. We're just making sure that we show the left-hand column of a two-column proof, basically. All right, so let's get to looking at this. We are going to prove through logic that sine cubed of x plus sine of x times cosine squared of x, all divided by cosine of x, is going to equal tangent of x. I'm telling you it's true. I'm telling you that this is the answer. Here's the problem. Here's the answer. Our goal is to show why it's true. So I'm going to use that trick I used just a few minutes ago of going down to a single letter for everything to see if that might help you identify something. So we have sine cubed plus sine cosine squared divided by cosine. Now keep in mind that tangent is just sine divided by cosine. So we'd love to get this to just sine divided by cosine, and the divided by cosine is there. But what a lot of people don't see is that there is a GCF right here. We can actually factor the numerator. And factoring is a great way to work on this. Because they both have an s or a sign, I'm going to factor that out. So that would give me, if I factor out a single sign, that would leave me with sine squared of x plus cosine squared of x divided by cosine of x. And if you recall, and we're still trying to prove that that does equal tangent of x, recall that sine squared of x plus cosine squared of x is a Pythagorean identity. So that really gives us sine of x times 1 divided by cosine of x. And again, we're trying to prove that that equals tangent of x. Notice how I keep bringing that what we're trying to get to down each time. Well, sure enough, sine divided by cosine is tangent. And tangent most definitely equals itself. So therefore, we are now done with the problem because we worked the left-hand side until we got to the right-hand side. The work is the answer. That's the proof. That's the, here is step 1, step 2, step 3, step 4. Could I add a column that says, given, factor out sine of x, use the Pythagorean identity, use the definition of tangent? I could. I'm not worrying about that in this video. I don't know if your professor will have you worrying about that, but that's one thing that could be done in the future. Okay? All right, let's try another one. This time we're going to verify. Sometimes they use verify instead of proof. That the cosine of mu over 1 minus sine of mu is equal to secant mu plus tangent mu. Okay, so this one's kind of a weird one, and it's probably one that you wouldn't think of the trick that I'm going to use. So I'm going to think about what secant of mu plus tangent of mu is. If you think about it, secant is 1 over cosine, and tangent is sine over cosine. So they're both over cosine. So if I could somehow get this to be over cosine, then that would be really, really beneficial to me. Okay. The other thing is that I know that sine squared plus cosine squared is 1. And therefore cosine squared of mu would be 1 minus sine squared. And you might be going, well, how in the heck is that going to benefit us? Okay. Well, if you remember, 1 minus s squared, I'm going to use that abbreviation there, can factor to 1 minus s times 1 plus s. We have 1 minus sine. So if we take this 1 minus sine and multiply it by 1 plus sine, we're going to get 1 minus sine squared, which is cosine squared, and we can start moving on from there. Just remember, whatever we do to the denominator, we also have to do to the numerator. So this information here is going to be our key to get this into that. And I'm sure many of you go, well, I would not have thought of that on my own. I get that. I completely understand that. That's why you're watching this video. So we have our problem here. I'm going to multiply both times 1 plus sine of mu. And yes, I am saying mu. It is a Greek letter. And I'm actually going to leave the numerator in factored form. I'm not going to go ahead and distribute that. And sometimes it's helpful to leave it in factored form. Sometimes it's helpful to distribute it out. I'm only going to distribute out the denominator. So it'll give us cosine mu multiplied by 1 plus sine of mu. And as we talked about, this is going to become, it's a difference of two squares. So the product will be 1 minus sine squared. And of course, we're still trying to prove that this is equal to secant mu plus tangent of mu. We're trying to make both sides look exactly the same. I just am choosing to work the left side. You could have worked the right side. So now we'll have cosine of mu multiplied by 1 plus sine of mu. I'm going to use the Pythagorean identity in the denominator, so 1 minus sine squared is cosine squared. Now, cosine and cosine squared reduces, so we'll have 1 plus sine of mu divided by cosine of mu. And I'm going to go ahead and work the other side right now. We know that secant is 1 over cosine. We talked about that a minute ago. And that this is sine of mu over cosine. So if I were to add fractions together, I would keep my common denominator. And there we have it. The left side matches the right side. So it is okay to work both sides, as long as you're keeping things equivalent. Could I have continued and wrote this line like this, and then after that wrote this? Absolutely. Absolutely, it would just look 2 lines longer and it would be the same thing, the same information, it's just written differently. Okay, so we definitely can get there. However you want to look at it is definitely a great way to approach it. We just have to make sure we take it one step at a time. So these are definitely going to be weird when you're practicing them because they take a lot of critical thinking. They're like, okay, what rule could I use? Do I have to use that rule? What if I did it this way? That's why I try to make sure that I keep it very simple, and I always go back to sine and cosine because I feel that does help us the most. Plus, if I'm just using sine and cosine, I can use the letters S and C, and that can keep me from making a lot of mistakes. Okay, so I am going to go ahead and work the left-hand side, and then I'm going to work the right-hand side. And I'm just going to go ahead and simplify each of them separately. So let's just focus at the left-hand side. Okay, and you're probably wondering why I go this route, and that's fine. You can do it a lot of ways. I'm going to separate these fractions out. That way it's not a numerator and a denominator. I'm going to do something a little different in this one. Okay, so that's the left-hand side. LHS stands for left-hand side. So 1 over cosine u could be rewritten as secant of u. And cosine divided by cosine is just 1. So that's another way of looking at the left-hand side. So if I were to work the right-hand side and get to this answer, it would be okay. I could say that that's the answer I have. If I get to this answer, then that's okay. If I get to that answer, it's okay. I just wanted to have the left-hand side written in multiple formats because the right-hand side looks more complicated to me because it's not in terms of cosine. It's got tangent and secant. So let's go ahead and let's take a look at that right-hand side. It says tangent squared over secant minus 1. Okay, well, again, as always, I'm going to go ahead and turn it into terms of sine and cosine. So we have sine squared over cosine squared over 1 over cosine minus 1. And I'm not super fans of the double fractions. So to clear out double fractions, I'm going to go ahead and I'm going to multiply the numerator by cosine squared and the denominator by cosine squared. Now when I multiply the numerator by cosine squared, the cosines are going to cancel out, and I'm just left with sine squared. But I'm going to have to distribute on the denominator, so cosine squared times 1 over cosine would leave me with just cosine. And 1 times cosine squared would make that. Now what I notice here is that I most definitely have a greatest common factor in the denominator. Okay, so I could look at it that way, but I know that the left-hand side was all based off the word cosine. So I either need to get it in terms of cosine or I need to get it in terms of secant. So I want to lose the word sine. So I'm going to use my Pythagorean identity there. We've shown it enough in this video that hopefully you know that sine squared is equal to 1 minus cosine squared. Okay, now everything is based in cosine, but I have exponents, which means I can probably factor, and that's what I'm going to do next. I am going to go ahead and factor the numerator. It's a difference of 2 squares. And I'm going to factor the denominator. It has a GCF. And at this point, I can notice that this and this will cancel. And I get to 1 plus the cosine of mu over the cosine of mu. Now you'll notice I didn't write down both sides the whole time, and it's because I abbreviated left-hand side and right-hand side. But if I come back up, now I can see that the left-hand side, or the right-hand side, is actually equivalent to the original left-hand side. Okay, so now I can conclude that the left-hand side did indeed equal the right-hand side. And by using LHS and RHS, it just saves me some writing, and I can use that abbreviation so I don't have to write both sides down 100% of the time. So that's all your goal in the beginning of working with trig identities is they are either going to give you a statement and they're going to say, hey, simplify this, or they're going to say, hey, disprove this, or they're going to say, hey, these are equal, tell me why. So in the beginning, just working with them, getting used to them, it's going to be one of those 3 scenarios, and it is going to require some critical thinking on your part. So I just want to go over a couple of definitions, just making sure you have these in case you've lost them or you forgot about them. So cosecant of x is equal to 1 over sine of x. Secant of x is 1 over cosine. Tangent is sine over cosine. Cotangent is cosine over sine. And please don't forget your angle inside these. That's very important because you will eventually get to where sine might be based off of alpha and cosine might be based off beta, and they'll be in the same problem. So make sure you're careful with your writing down of your work, because that's going to be a really, really big thing moving forward as you continue to work with trig formulas. We've talked about it multiple times here, but I'm going to go over it. Cosine squared equals 1. Now, if you take the purple equation and you divide it by sine squared, it will be 1. Cosine divided by sine is cotangent. And 1 divided by sine is cosecant. So that is another Pythagorean identity you can use, and it's because we took the purple value divided by sine squared. If you were to go back to the purple equation, instead of dividing by sine squared, you divide it by cosine squared. That would give you sine squared divided by cosine squared is tangent squared. My pen didn't want to work. Cosine divided by cosine is 1, and 1 divided by cosine is secant. Okay, so there were several strategies in here, whether you just use a single letter, putting everything in terms of sine and cosine. The single letter strategy I would only use if you're in terms of sine and cosine, because if you're using cosecant, secant, cotangent, especially if cosecant and cotangent are in the same one, that single letter is going to confuse you a bit. So please make sure that you're only doing that if you're in terms of sine and cosine, or if you're super, super careful and reasonable and responsible with it. It's just a strategy to do some side notes. It's not a replacement for the true trig work. So hopefully this helps out, and again, you'll probably be introduced to additional formulas in your near future.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.